Hi, this is the presentation of Teamforce Progress. I'm Jin Lee. First, I will briefly introduce the paper and two main tasks. Then Myunghwa will show the replication of DM control. Lastly, Jungmin will explain the replication of Chromase and improvement plan. The topic targeted in this paper is that a policy trained in one environment might not generalize with other new environments. It can fail the test if the environments change, even if a policy is trained well. So this paper proposed a method for adapting a policy in a new environment that does not provide a legal signal. The proposed method is called PAD, which stands for Policy Adaptation During Deployment. It learns a policy in a single training environment and deploys the policy in a target test environment, and then it adapts the policy during deployment itself. PAD does not require data prior to deployment, nor does it assume to access the reverse signal at test time. Instead, PAD only uses data collected during deployment and adapts online using a self-supervised training signal. This can be done by introducing self-supervision to obtain free training signals during deployment. PAD algorithm consists of training phase in a fixed environment and the adaptation phase during deployment in the target environment. In training phase, policy is jointly trained by optimizing the RL and self-supervised objectives. In adaptation phase, policy is adapted with optimizing only the self-supervised objective and observation are collected from the test environment online. In this paper, two different self-supervised tasks are considered. First one is the inverse dynamic model. It takes the states before and after transition and predicts the action in between. So it is useful for tasks that require motor control. And the other one adopts a rotation prediction task. An observation is rotated by one of four different angles and casts this as a four-way classification. So it is more suitable for tasks that require scene understanding, such as navigation tasks. In network architecture, one can think of PHY-E as a feature extractor. Self-supervised has PHY-S as a model on the feature space, and RL has PHY-A as a controller based on these features. In short, PAD updates PHY-E during test time using gradient from a self-supervised task, so that PHY-E can generalize. Observation are stacks of colored frame cropped to smaller sizes. PHY-E consists of 6 or 8 convolution layers and output features with different size depending on the task. PHY-S and PHY-A consist of 3 convolution layers followed by 3 fully connected layers. Implementation of policy and value function depends on the learning algorithm. In simulation, we evaluate the PAD and baseline on two tasks. One is DMind control, which is a collection of continuous control tasks where agent only observe low pixels. Generalization benchmark on DM control represent diverse real-world tasks for motor control. The other one is Chromase. It is a discrete action 3D navigation task for Wisdom, in which an agent is to navigate a maze and collect objects.
This was our replication plan. We proceeded with DMC control replication as planned. In the case of Chromase, it was slightly delayed since the code is not available. And in both cases, training took more time than expected, so there were unexpected variables. For DMC control tasks in the paper, 9 tasks of 6 domains were mainly tested and discussed for evaluating the PAD. Therefore, we also focused on these tasks for replicating the paper's results. To evaluate the generalization performance of the PAD, we focused on the following 2 test environments, randomized colors and natural videos as background, which were mainly considered in the paper. We set up the environments for DMC task by referring to the original paper's code and replicated the experimental results with the hyperparameters used in the paper. Referring to the experimental result of the paper, we considered these 4 models as our baselines. For all tasks of the EMC, the paper's results show that the self-supervised task IDM was better than the rotation task. We wanted to confirm this for our improvement step. In addition, we tested the PAD version of each model to evaluate the generalization performance of the PAD. First, we conducted experiments on randomized colors. These experiments show whether the PAD can adapt in stationary environments. These are the results. Except for the three tasks, the PAD version of SAC plus IDM show the best performance as in the result of the paper. The plus and minus of rewards indicate the mean and standard deviation for 10 seeds. Since an experiment on a single seed takes 2 to 3 days, we couldn't experiment with all the seeds. Therefore, there are some numerical differences in rewards. However, as the result of the paper, we could observe that IDM shows relatively better performance than the rotation, and PAD is helpful to improve the generalization performance. In addition, we could observe that PAD is more helpful to IDM models. These are our simulation results of the PAD version of the IDM models. As you can see, except for the work task, it can be seen that most of the tasks were trained and adapted well in the stationary environments. In the case of the work, we are checking the performance with other seeds. Next is experiments on video backgrounds. These experiments show whether PAD can adapt in non-stationary environments. These are the results. In the paper, experimental results of the rotation models were not presented. Therefore, for comparison, we also presented and evaluated only the IDM model. In the future, if necessary, we will also test and rotation models. As you can see, as in the paper, PAD version shows better performance in most of the tasks. However, some rewards of our results differ greatly from the results of the paper. In addition, some of the PAD version didn't significantly improve the performance. In the GitHub, these 10 video backgrounds are provided. One of these is used for one evaluation. However, we couldn't find which video was used as the background in the paper. Therefore, we couldn't replicate the paper's results completely. In addition, like the stationary environments, there may be a difference by seeds. These non-stationary environments still seem to require more experiments.
And next, I will talk about our progress for the replication of CureMaze. In this case, since there was no available source code which adapt PAD to CureMaze, we asked the author for the related codes or guideline. Fortunately, we could get the codes, but it is not working well, so we replicated the experiment by debugging the code and modifying the parts that did not work. The experiment environment was set on these dependencies, and the hyperparameter was set as the same as the paper. However, we could not run episode length as 1000 because it required excessive GPU memory, so we reduced it to about 1/10 where we can perform experiments. Different light and texture settings were considered to measure generalization in test environments. We also considered both of them, but for texture, we only considered the words. The experiment baselines are the same as the mind control experiment, but the important difference is that its Bayesian learning algorithm is A to C. Training was performed on only one environment, and the learning went well as the episode progressed as shown in these videos. Based on the trained model, we performed evaluation on new environments having 3 different textures, brighter and darker. These are the results of evaluation. The numerical difference is natural due to the adjustment of episode length, but even considering it, our results were very different from those in the paper. In paper, A to C plus load with the PAD showed the best performance, but it was not in our experiments. In addition, the standard deviation was so high that it was difficult to be sure if this was a meaningful result. In recorded videos, we can see that applying IDM shows better performance. We are debugging to find problems in our experiments. Since the code is not a released version, it seems that GPU memory and the resources are excessively used. Even our server went down for a while during the experiment, so we are focusing to reserve memory and resource leak. While debugging it, we are also starting to implement for improvement. According to our paper, selecting a proper self-supervised task is crucial to the success of PAD. Based on it, we want to find a task that enables PAD to perform better. There are 2 approaches for it. First one is modifying the original task. In our paper, raw task is performed with a single randomly rotated image. However, according to the Ronna paper, fitting all the 4 differently rotated images to a model simultaneously is more helpful. We expect that it can have better performance than original route with PAD. The second approach is introducing a new task. In the last proposal, we suggested SimCurl as a new task. However, we thought this will be hard to be adapted to PAD. That's because in SimCurl, concursive learning learns the features using concursive loss between the transformed views of the same images and different images. However, in our experiments, it is hard to get proper different images. So we have performed additional solvable new tasks. And as an example of this, we are considering to apply PAD to tasks that generate random augmentation from input images and predict which augmentation was applied. We were inspired by Red paper applying augmentation to reinforcement learning, which shows excellent data efficiency and the successful generalization. The next one is our implementation plan for improvement. We will proceed with these 2 tasks in parallel before final presentation. These are our references. Thank you for your attention. Thank you.